Section 7.1 Sets. A set is a well-defined collection of objects. The items in the set are called elements or members. Let's say we have the set 3, 4, 5. We can say that 4 is an element in set 3, 4, 5. So this little symbol here means is in. But 2 is not in set 3, 4, 5. If there are no elements in a set, we call it the empty or null set, and we represent it with a 0 with a slash through it. We can use set builder notation to help build common properties rather than listing all of the elements. So set builder notation basically is this part here, where it has these braces at the end, and we have x such that, x is a natural number less than 5. So what are those numbers that are natural numbers less than 5? And remember, natural numbers are counting numbers. Those that we can count with our fingers. So the counting numbers less than 5 are 1, 2, 3, and 4. And then we just include the elements in braces. Write the elements belonging to the set X such that X is a state that borders Florida. So states that border Florida are Alabama and Georgia. So the elements in our set are Alabama and Georgia. Note that Minnesota would not be in the set. So we would say that Minnesota is not in the set X such that X is a state that borders Florida, etc. Sometimes every element of one set also belongs to another set. For example, if we have the set A, which contains the numbers 3, 4, 5, and 6, and we have the set B, which is 2, 3, 4, 5, and 6, notice that each element in A, we have 3 and 3, 4 and 4, 5 and 5, 6 and 6. Notice that each one belongs to the set B. This means that set A is a subset or a smaller set of set B. So set A is a subset of set B, written A is a subset of B. So using the little symbol here, if every element of A is also an element of B. So we would write, just as we have here, that A is a subset of B if every element of A is also an element of B. Set A is a proper subset of B, so A is a proper subset. A proper subset, notice it doesn't have the little line underneath. If A is a subset of B and A does not equal B, since A does not equal B, meaning they don't have the exact same elements, we would say that in our example above, it is a proper subset. If we want to indicate that A is not a subset, so they're not a smaller set, we would write that A is not a subset of B. So let's determine whether the following statement is true or false. Is the set 3, 4, 5, 6 equal to the set 4, 6, 3, 5? So notice on the left they're written in numerical order, but on the right they're not. But they do have the same elements of those sets. So 3 and 3, 4 and 4, 5 and 5, 6 and 6. So yes, this statement is true. Is 5, 6, 9, and 12 a subset of 5, 6, 8, 9, 10, 11? So remember, a subset, they have to contain all of the same elements. So we have 5 and 5, just a smaller set of those elements. oh, there's no 12 here. So 12 is the odd man out. So this is false. It's not a subset. So we would say that is not a subset. Note the empty set is always a subset of a set. So it doesn't matter what set it is, it's always a subset. And note that the set itself is a subset of it. So, what are the possible subsets of if we have a set 7, 8? So we just said that the empty set is always a subset, so there's 1. If we had 7 by itself, that's a smaller set of 7, 8. Similarly, we could have 8 by itself, which would be a subset of itself. And then the set itself is a subset. So we have 1, 2, 3, 4 sets that are possible subsets or smaller sets of set 7, 8. What are the possible subsets of the set A, B, C? First, we have the empty set is always a subset of it. We could do each individual by itself. We could do combinations, so A, B, A, C, and B, C. And then finally we could have the set A, B, C. That's always a subset of itself. As you can see, by raising the amount of elements we have, drastically increases the amount of subsets we can have. So the number of subsets, a set K of distinct elements, so each individual element has 2 to the K power subsets. How many subsets would the set 3, 4, 5, 6, 7 contain? So we're going to take 2 to the power. We have 1, 2, 3, 4, 5 individual elements. So 2 to the 5th power would result in 32 subsets. All right. How many subsets would X, such that X is the day of the week, contain? Well, there are 7 unique days of the week, so we'll take 2 to the 7th power, which would be equivalent to 128 subsets. That is a lot of subsets. How many subsets would the empty set have? Well, the empty set has no elements in it. So 2 to the 0 power, and remember anything to the 0 power is equal to 1. So it would have 1 subset. And the empty set would have the set, just the empty set itself would be our set. So let's use Venn diagrams to help with sets. Below is a picture of a Venn diagram, a way to visually see sets. So notice we have this U here in the corner. This means and then everything else is in this. So U is the universal set. Well, what is the universal set? It's the set of all elements. So every element is in this set. Okay? And we can see that there is a circle within the circle B. So A is a subset of B, is what this is saying. So A is in B. The complement of a set. So A with this little apostrophe here is called a complement. It means elements not in A. So the rectangle again represents the universal set. We want the elements that are not in A. Well, if they're not in A, they're around here. So they're in the universal set. So A, if X is not in A, then X is in the universal set. I know that's kind of weird. So let's practice this. So let's say we have the universal set contains the numbers 1 through 11. We have a set A that has 1, 2, 3, 5, and 7, and set B that is 2, 4, 5, 7, 9, and 11. Find A prime. So the complement of A, meaning we are looking for the elements that are in the universal set that are not in A. So A prime is equal to, well, 1 is already in the universal set, so we can't include that. 2 is already in the universal set in A. 3 is in the universal set, but not in A. 4 is in A, 5 is in A, 6 is in the universal set, but not in A. 8 is in the universal set, but not in A. 9, 10, and 11 are all in the universal set, but not in A. Find the complement of B. So we're looking for the elements that are in the universal set, but are not in B. So 1 is in the universal set, but not in B. 2 doesn't work. 3 is in the universal set, but not in B. 4 can't work, 5 can't work. 6 is in the universal set, but not in B. 7 won't work. 8 is in the universal set, but not in B. 9 won't work, but 10 will. All right. Find the empty set complement. So we're looking for the elements of U in the universal set that are not in the empty set. Well, if it's not in the empty set, it must be all of the elements then, because there has to be something in the set. So the empty set complement is equal to the universal set, all of the items. And then as a side note, the complement of A complemented is the set itself. So anytime we see a complement to a complement, they kind of cancel each other out, giving us the set itself. So if we have the complement of B and we want to take the complement of that, these ideally cancel out, giving us just the set itself. Let's say we want to intersect two sets together. So let's say A intersect B. So this symbol here means to intersect. So we want to find those things that are in A and they are also in B. So they're in set A and at the same time they're in set B. So what are those things they have in common? So let's say we have the set 3, 6, 9 for A. And the set B is 2, 4, 6, and 8. And we have the universal set 0 through 10. Find A and B. So A intersect B. So what are the numbers that A and B both have in common? So they don't have, they don't have 2 in common. They don't have 3 in common. They don't have, they have 6 in common, it looks like. So it looks like the only number that they have in common is 6. So A intersect B is the set 6. 6 is the only number that they have in common. Erase this for now. We'll come back to that. Let's find A intersect B complement. So first of all, let's list what A is. A is 3, 6, and 9. We want to intersect that with those items that are not in B. So those items that are not in B are, so if we compare B to the universal set, they can't be in B, so the leftovers are 0, 1, 3, 5, 7, 9, and 10. So now that we have A and we have the complement of B, what are the items that they share in common? So it looks like they share 3 in common and they share 9 in common. Those are the only ones that they share in common together. So 3 and 9. Let's find the intersection of A complement and B. So first of all, let's try A complement intersect B. So we want to find those items that aren't in A and that they share in common with B. So let's first determine what items are not in A, but are in the universal set. So the items not in A would be 0, 1, 2, skip 3, 4, 5, skip 6, 7, 8, skip 9, and 10. We'll intersect that with the items in B, 2, 4, 6, and 8. And we want to determine what they have in common. So it looks like they have 2 in common, 4 in common, and 8 in common. So when I intersect those together, their intersection that they share in common are 2, 4, and 8. So disjoint set is if we were to try to intersect them together, and notice that in our universal set we have set A and B and they don't overlap. So disjoint sets means they have no elements in common. But what about what unioning sets A and B? So instead of the intersecting, let's union them. So we consider them A union B to be items that are in A, or items that are in B, or items that are in both of them. So everything combining all of their elements together. So let's say we have the set A is 1, 3, 5, 7, 9, 11, and set B is 3, 6, 9, and 12. And we add in a third set, 1, 2, 3, 4, 5, and we have the universal set 0, 1, 2, 3, etc., all the way through 12. So let's find A union B. So combining the items in A with the items in B. And we only need to write them once. So if they have items that occur twice, we only need to write them once. So the set A is 1, 3, 5, 7, 9, 11. And set B is 3, 6, 9, and 12. And we want to find out what they have all together, so combining their units. So we have 1 is what they share. With neither of them have 2, so we skip 2. They have 3. It has to contain, there's no 4 in them, so it has to contain 5, has to contain 6, and 7, and 9, 11, and 12. So combining all of their units together. Let's find A union B, so combining A and B together, and intersect that with items that are not in C. So we're going to combine A and B together and intersect that. What do they have in common with the items that are not in C? Well, we already have A union B. We already discovered what that was. So we can write that. No extra work needed here. And let's intersect that with the items that are not in C. So if they're not in C, we have to compare them to what the universal set. So we can't have 1, 2, well, we can have 0 because 0 is not in C. We can't have 1, 2, 3, 4, 5, but we can have 6, 7, 8, 9, 10, 11, and 12. And now we want to intersect them. So what do they share in common? What do they share in common? So it looks like they don't have 1 in common, 2 in common, 3, 4, 5. They got 6 in common. Looks like they have 7 in common, 9, 11, and 12. So the items that they have in common are 6, 7, 9, 11, and 12. Okay, the last one here. Find A union B intersect not in C. So let's first tackle this part here, and then we'll union it with A. So we have items in B, which are 3, 6, 9, and 12. The items that are not in C, we listed over here. So the items not in C are 0, 6, 7, 8, 9, 10, 11, and 12. So it's asking us to find what do they have in common. So they have 6 in common, 9 in common, and 12 in common. So 6, 9, and 12 in common. We want to union that, combine that with the elements of A, 1, 3, 5, 7, 9, and 11. So we need to create a set that contains all the elements from A and all the elements of B intersect not in C. So it has to have 1, 3, 5, 6, 7, 9, 11, and 12. So those are all the elements that are in A and all the elements that are in B intersect not in C. So do the parentheses portions first before you try tackling the outside piece, especially when it has 3 items all working together. And this is the conclusion. Oops, not quite yet. We have one more slide to go. I apologize. One more slide. So an application problem. The tables below show 5 of the largest holdings of 4 mutual funds on May 21st, 2014. We have Vanguard, Fidelity, Janus, Perkins large cap value, and then the White's value fund. So it says, let U be the smallest possible set that includes all the corporations listed, and VFJW be the set of the top holdings. So V is going to represent Vanguard, F is going to represent Fidelity, J will represent the Jerkins group, and then W will represent the White's value fund. So we want to find V intersect J. So we're going to look at these two here. We want to know what companies they have in common. So which ones do they have in common? So they don't have Apple in common. Oop, it looks like we have Berkshire in common. So Berkshire. And I'm not going to write the Hathaway, we'll just kind of shorthand it. They don't have Google in common. They don't have Microsoft in common. They do have Wells Fargo in common. So they had Berkshire in common and they had Wells Fargo in common. The top one doesn't have AIG, Citigroup, or Pfizer. So the only items, if we were to intersect them together, the only items they have in common are Berkshire and Wells Fargo. Let's find J, so the Janus Perkins group, unioned with F, so the Fidelity group, and then find the complement of them. So let's first deal with the parentheses. So we want to find J and F. So what companies do they, when we put them all together, make the large set? So it has to contain AIG. It has to contain Google. Has to contain Microsoft. It has to contain Verizon. It has to contain Wells Fargo. So those are all the items from the F group. So let's look at the J group. You could have done the J group first. It doesn't really matter. So we already took care of AIG. Google isn't in this list. We took care of Microsoft. That's not in this list. Verizon's not in this list, but Wells Fargo is in this list. So we need to add Berkshire, Citigroup, and we need to add Pfizer to the list. So these are all of the groups of J union F. So combining the groups of F and J together. Now the last part we need to consider is now we need to find the groups that are not in this group. So I'm going to start over my eraser here because it shouldn't be too many that aren't listed. So we want to find items in all of these lists that are not listed already. So if we look, so AIG is already included, so we can get rid of AIG. We can get rid of any place where we see Google. We can get rid of Microsoft, anywhere we see Microsoft. We can get rid of Verizon, so anywhere where we see Verizon, we can get rid of Verizon. We can get rid of Wells Fargo. We can get rid of Berkshire Hathaway. We can get rid of Citigroup. And we can get rid of Pfizer. Which means that the items that are not in J Union F are Apple, Apache, DirecTV, and Texas Instruments. So our solution is Apple, Apache, DirecTV, and Texas Instruments. So this part here, this part included J Union F. And then when we did this last part, we want the items that are in the whole set but are not in J Union F, which would be this part here. Now this concludes section 7.1 on sets.